We're going to talk intro to polynomials. Today is a lot of like informational notes, so we'll take them down. We'll do some examples. You'll have a homework assignment, but it's the foundation, so we're all working with the same set of vocab as we progress through the chapter and talk about our polynomial. So first things first, answer to Mason's question, what are polynomials, right? Polynomials are functions that are made up of many terms. That's what poly means, right? Polygons in geometry had many sides. Now, you did know about some special polygons, like triangles, quadrilaterals, pentagons, hexagons, octagons. When they get a special name, we know exactly how many sides it would have. So you actually know some names of polynomials. So we've worked already, if you think back to chapter 3, we worked with a binomial, and we worked with a lot of trinomials. A binomial has how many terms?
2.
A trinomial has how many terms? 3. So you already know a little bit about some polynomials. So it's a function made up of many terms. The terms include coefficients, variables, usually x, but we could use any variable, and exponents. So in this function that I have at the bottom of the screen, f of x equals 2x cubed minus 5x squared plus x. 2x cubed is a term. Negative 5x squared is a term, and x is a term. Each term has a coefficient, so the x cubed term's coefficient is 2, the x squared term's coefficient is negative 5, and what's the coefficient to x? 1, okay, so there must be a plus 1 there. They have variables, although not every term has to have a variable. I could add on the back here, I could do a plus 1, and then I have a constant term, which we're going to talk about on the next slide. But technically it does have a variable, it's just x raised to the 0, and anything raised to the 0 is equal to 1, so then the x goes away. And then they each have exponents as well, so cubed, squared, x to the first, x to the 0. Every term has an exponent. Notice that how can you tell the difference between terms? Terms are things that are added and subtracted. Factors are things that are multiplied. Okay, so we're looking at many terms, many things that are being added or subtracted. If I take off my constant term and go back to my original, how many terms does this polynomial have? 3 terms, so we would identify it as a trinomial. Okay, so it has 3 terms. Okay, so is it a polynomial?
The first one?
Yeah.
No.
Why not?
Because it's dividing.
Dividing by x. So I'm going to go back here, and we're going to say a few more things about terms. Okay, notice in my terms I had like 2x cubed, negative 5x squared, x to the first. I can even have an x to the 0. But make a little note to yourself. Exponents must be whole numbers. So whole numbers are numbers like 0, 1, 2, 3, etc. So we can't divide by x. We can't have any negative exponents. We can't have any fraction or decimal exponents. So all of our exponents have to be whole numbers. Oh, EXP apostrophe T. I don't know if I've written that yet in this class. That's because I'm lazy and I don't want to write the word exponent. But if you want to write the word exponent, or you won't be able to read that later, then you should write out the whole word. So let's go back and look at what Rihanna was looking at. H of x equals 2x plus 1 over 5x. She said that's not a polynomial because you're dividing by x, and I agree. This would be a no. Divide by x. Not okay. What about g of x? Let's see, what does g of x say? Negative 2/3 x squared plus 3x to the 4th minus x times the square root of 2 plus 1.
No.
Why do you say no, Mason?
It has a fraction exponent.
Where?
Oh wait, no. It's not a whole number.
What's not?
The first term.
The first term has a fraction as its what? Coefficient. Would you agree with that? At first you said it has a fraction exponent, and then you kind of backtracked, right? Does it have any fraction exponents? No. If we focus on the exponents, our exponents are 2, 4. What's the exponent to this one? 1. And then this is like x to the 0. Is that a polynomial? Yeah. Did I say any rules about your coefficients? No. You can have fraction coefficients. You can have negative coefficients. You can have decimal coefficients. And you can have irrational coefficients. Square root of 2 is like 1.41. Doesn't follow any kind of pattern. Keeps going. So, yeah, this is a polynomial. All of the exponents are whole numbers. So you can have a polynomial that doesn't look really nice with its coefficients, but its exponents will be good. Okay, so have a little chat with your new table group and see what you guys think about P of x. P of x, I know it's at the bottom, so it's a little hard to see, is pi x to the 5th minus x to negative 1 plus 7 minus x squared. So talk to your group for me. Bless you. All right, Max, what'd your group say?
No.
No, why not? Why? Okay, so we're going to talk about form on another slide, but just is it a polynomial? You're saying all the exponents are whole numbers? Can you give me examples of whole numbers? Is negative 1 a whole number? Whole numbers are what? They're only positives and 0. We call the only positive numbers that are nice numbers, natural numbers, or your counting numbers, like you start counting at 1, 2, 3, 4. Those are called your natural numbers. Whole numbers include 0. What are the numbers that include the negatives called? Integers. So negative 1 I classify as a nice number, but it's an integer value. Okay, so I would say no. It has a negative exponent. Wasn't that on my list of things that are not allowed? Negative exponents, dividing by x, fraction exponents. Okay, those are not allowed. So you're going to have some problems on your homework assignment at the very beginning of that homework assignment, like 3 through 8 or whatever, where it's going to say, like, is it a polynomial? And if the answer is no, you're done. Like, I'm not going to have you do anything else with that polynomial. But if the answer is yes, I'm going to have you name off some other parts of the polynomial. So now we're going to get into some other things where Aiden was mentioning a form of a polynomial. So we're going to talk about those things next. Okay. So let's talk about polynomial vocab. Now I put an example up here just so that we can use this example to point out what it is I'm talking about. So if you want to write this example in your notebook so that you have it to look at, you could do that. But we could apply this to any polynomial. It doesn't have to be this polynomial that I have on the board. Now, as your math teacher, I'm going to request that you always keep your polynomials in something called standard form. Mathematicians have a lot of things they call standard form because then Elise's equation looks like Ashlyn's equation looks like Colin's equation, right? All the mathematicians would write it the same way. Okay. So we're all going to agree in this room to keep things in standard form. And standard form means that exponents decrease from left to right. So you put your highest exponent at the front, you put your lowest exponent at the back, and think about what we called standard form in quadratics, ax squared plus bx plus c. Isn't that the case? Its exponents are in descending order. Yeah, you could keep going. You could add more and more. We could do ax to 26 plus bx to 25th plus cx to 24th. Wouldn't that be fun? All right, a degree. A degree is just called your highest exponent. So degree is really important. We're going to see this over and over and over again in chapter 4. You're going to know degree super well. So the sooner you get it, the better off. It's just the highest exponent. The leading coefficient is the coefficient for the term with the highest exponent. Which would be your degree. So you're going to see me throughout chapter 4. I'm going to write leading coefficient as LC. And that's going to be another important thing for us to identify. And so the LC always goes with the degree. They're in the same term together. To identify the degree and the leading coefficient of your polynomial, you're looking at a single term, the term with the highest exponent. Now, let's look at our polynomial just real quick, f of x. Is our polynomial in standard form? Yes, it's in standard form. Exponents are decreasing from left to right. 3, 2, 1, and then for the constant, it's 0. Okay. If your polynomial is written in standard form, where will your degree and leading coefficient be? At the very first term. So think about how nice that will be if we all agree to write in standard form. We'll all know exactly where to look for our degree and our leading coefficient. So what's the degree of this polynomial? 3. And what's our leading coefficient?
0.
If it were 0, there wouldn't be an x cubed term, right? Okay, so remember, if you see there's an x cubed, there's 1x cubed. All right, and then I mentioned this previously, and I think we're probably on the same track here with a constant. The constant is the term that doesn't have what? X.
So 5. -5?
Yep, -5. Okay. If it doesn't have an x, x is the variable, the thing that varies. So if it doesn't have an x on it, it never varies. It's always the same thing. It's always going to be -5 at the end. No matter if x is equal to 1 or x is equal to 3 or x is equal to 1 million. You're going to have -5 at the back of that polynomial. All the other terms will change when you plug in different numbers. And we could label, Mason gave it to me, the constant is -5. Okay. So notice that in this polynomial there are some other terms, x squared, -x squared, and plus x. They don't have anything really special. I mean, I need them if I'm going to evaluate the polynomial. I'd have to plug into those x's. In terms of identifying things, if we're in standard form, you're going to be looking at what I'll call the bookends of your polynomial. At the front, you'll find your degree and leading coefficient. At the back, you'll find the constant. Okay, we okay so far? Have you talked about degree and leading coefficient at all ever in Algebra 1? Does anybody think this is familiar? Some people are maybe saying yes, but a lot of people saying no. Okay, that's good. It's always hard for me to remember. Okay, so those are just some of the parts of the polynomial, how we name them and what we're going to call them. Now I'm going to talk about in the next 2 slides what the equation can tell us about our graph. So tomorrow we're going to be graphing polynomials. Today we're just going to be looking at like what kinds of things can we pull from the equation. Just by looking at the equation, we know these things to be true. Okay, so on this slide I'm going to talk about the type of polynomial that it is. I'm going to talk about the total number of zeros. I'm going to talk about the maximum number of turns, and that's a y-intercept at the bottom. Okay, so think back to geometry when you were learning about polygons. I mentioned this before. You had a bunch of names for the different polygons, right? Triangles, quadrilaterals, pentagons, hexagons, heptagons, so on and so on. So we have some special names for some of our polynomials. So the type is based on the degree. And what's our degree again? Our highest exponent. I got to calibrate my board. Sorry about this. Okay, so if we have a degree of 0, and that's my highest exponent, what do we know about anything raised to 0? It's 1. So if x were raised to 0 and then it just equaled 1, there wouldn't be an x. It wouldn't vary. It would be a constant function. So anytime your degree is 0, we call it a constant function. Anytime your degree is 1, we've already studied those. Those are called linear functions. Y equals mx plus b is mx to the first plus b. It's a binomial. So it's a polynomial. It's linear. We've also done degree 2. What do we call degree 2? Quadratic. That was our last 2 chapters. In standard form, quadratics would be ax squared plus bx plus c. But we can also see the quadratics in other forms like vertex form or intercept form. But we know that once we FOIL that out, hopefully you realize this in the Mario project, once you FOIL it out, you get standard form, right? Quadratic, x squared. Does anybody know what we're going to call things with degree 3?
Triquatic.
Close. No.
Tri.
I mean, like, good try. Tri usually means 3. What's another thing that means 3? Trace. To cube something. So we call it a cubic.
Cubic centimeter.
Yeah, when you do like volume of different objects in science class, you're talking about cubic centimeters of water, things like that. 4, this can be a little bit tricky for people because it's similar to quadratic, but it's quartic. For 4, I really focus on that it sounds like a quarter. Right? 4 quarters in a dollar. Quartic. And the last one I'm going to give you is 5. Quintic.
Quinceanilla.
Now, do you remember what happened if you did like a polygon with 20 sides? What did you call it? An n-gon, a 20-gon, right? So if we go beyond these first 5 degrees in polynomials, then we just say 6th degree polynomial, 7th degree polynomial, 8th degree polynomial. But if I were to say a quartic polynomial, you'd be thinking in your head degree 4. Okay? So you would make connections of these names, but if it doesn't have a name, it would just be, or if it's too large, it would just have the number, 7th degree. Okay. So total zeros is equal to the degree. So the degree is what again?
The highest exponent.
The highest exponent. So like think about that. When we find the highest exponent, when we find the degree, so far we can name the type of polynomial that it is, and now we can also name how many zeros it will have. Okay. Another word for zeros is the word solution. So that's my abbreviation for the word solution. Again, I'm too lazy to write it out. SOL''N. If you don't know what that means, write out the whole word solution. And I'm going to say this here. We'll come back to this a little bit later. But real zeros, we know this from quadratics, are x-intercepts on the graph. What if one of our quadratics had 2 imaginary zeros? What did the graph look like?
Then it would open away from the x-axis.
It would open away from the x-axis, like it might be above the x-axis and open up, or it might be below the x-axis and open down, and it wouldn't have any x-intercepts. So we may have eventually some polynomials that would have imaginary zeros. So you might not be able to count all the zeros on the x-axis, but they still exist. They're just imaginary. So that's just kind of something we'll play around with. That's later in the chapter when we get to that. Okay, but we'll say that today. Okay, and then maximum number of turns is related to the number of zeros that you have. The number of zeros has to be equal to the degree, so you can't turn more than that many times that you would have to cross the x-axis again. So the maximum number of turns is equal to the degree minus 1. Maximum number of turns is equal to the degree minus 1. So think about this. Think about a quadratic. What's the degree of a quadratic again?
40.
Well, what's the degree of a quadratic function?
2.
2. Quadratic. The ones we just studied.
Not quartic.
Not quartic. Quadratic is 2. Degree 2. What was the shape of all those quadratics in the last 2 chapters? Parabolas. Okay. How many turns does a parabola have?
1.
1. So that's the degree minus 1. Think about a linear function. What's the degree of a linear function? 1. What's the shape of a linear function?
A line.
A line. How many times does a line turn?
0.
0, never.
So a cubic would have 2 turns?
A cubic could have 2 turns. So the key word here is maximum. It could turn twice, but it doesn't have to turn twice. I'll just take everything. Okay, it could turn twice, doesn't have to turn twice. Okay, and then the last thing on this one is the y-intercept. Okay, let's just take a moment to think outside of this whole polynomial stuff that we're talking about. Just think about y-intercepts in general. Where are the y-intercepts on a graph? On the y-axis. What's special about all the points on the y-axis if you look at their ordered pairs? X is 0. So if you were to plug 0 in for x in your polynomial, what would it equal? The y-intercept. And what's the only thing going to be left over when we plug 0 in for all the x's? The constant. So the y-intercept is equal to the constant. Now you can make a little side note in the margins of your notebook if you want that. I mean, essentially, you're also plugging 0 in for x. So, like, even my pre-calculus students sometimes have a hard time with intercepts. They're like, but how do I find the y-intercept? How do you find any y-intercept? Like, if you get stuck, if you don't remember that it's the constant, just plug 0 in for x. So if you want to write that in the margins of your paper, you could do that so that you can remember it later. Okay, we're doing okay so far? All right, I think, okay. A few more things that we can determine from the equation. Okay, there is something called end behavior. End behavior, it describes how the ends of your graph look. So I'm just going to draw 3 pictures of 4 pictures. 4 pictures of 4 different polynomials. Polynomials are curvy shapes. And when we talk about end behavior, we're talking about what are the different sides of the graph doing. Okay, so you have ends. You've got a right end and you have a left end. I like to think about the ends of my polynomials as my arms on my body, okay? So if I am modeling this first one, what's my right side doing? Going up. We're going to say rise. What's my left side doing? Going down. We're going to say fall. So this side's rise, this side falls. Okay, so I'm going to label that. Rise, fall. Okay, if I'm this polynomial, what's my right side doing? Falling. Left side is rising. If I'm a parabola, rise, rise. Right? My end behaviors are doing the same thing. So notice in the previous 2, the end behaviors were opposite of each other. In this example, they're doing the same thing. And then in this example, they're both falling. So if we talk about end behaviors or like the arms of your body, that they're rising or falling, those are really the only 4 options for what your end behavior could do. Fall, rise, rise, fall, 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 rise, rise. Okay. So we're going to use mathematical notation to describe these things. As x approaches infinity, means right side. What can I say to mean left side? As x approaches,
The top of the graph.
well, what would be the left side? Negative infinity. Make sure you're jotting this down in your notebook. You're going to need to know this mathematical notation. This is probably the hardest part. As x approaches infinity is going to be our word for right side. As x approaches negative infinity is going to be our word for left side. And then we're going to describe what y is doing. So y can go towards positive infinity. What would that mean your graph is doing? In terms of your arms? Rising. If y was approaching negative infinity, then your arm is falling. Now, if you have a picture of a polynomial, like I drew those 4 pictures just so we could kind of understand what end behavior was describing, then you can name those things using the mathematical notation. But what we want to know is how can we tell the end behavior without looking at a graph? What if we're looking at the equation? So that's what the leading coefficient test does. So for the leading coefficient, you're going to do right side first as x approaches infinity. A positive leading coefficient means the right side rises. A negative leading coefficient means the right side falls. Where's the leading coefficient? In a polynomial, what's the leading coefficient?
I want the highest degree.
The coefficient in front of the term with the highest degree, right? So normally if we're in standard form, it's going to be where in your polynomial? At the very beginning. So you're going to look, as long as it's in standard form, is it f of x equals a positive? Then the right side goes up. If it's f of x equals a negative, then the right side goes down, as long as it's in standard form first. Now, step 2, you're going to do the left side. It's called the leading coefficient test. You look at the leading coefficient for the first part of it to determine what the right side does. But for the second part, you're going to look at the degree. If it's an odd degree, the left side is opposite. If it's an even degree, the left side is the same. I like to underline O and O there. That's how I'm going to remember. I say odd is opposite, even, everything's the same. So I even have an E there, but I have to write everything. So if you do the right side, and like let's say it's f of x equals a positive, then the right side is rising. You can put your hand up in the air if you need to when you're doing your homework tonight. Okay. And then in order to decide the left side, you're going to look at the degree, which what's the degree again? The highest exponent. And you'll be looking at the highest exponent. All the exponents will be positive, right? Because they're whole numbers. Positives or zeros. So So you won't have to be looking if it's positive or negative. You're going to be looking if it's even or odd. If it's even, then what's your left side doing?
Stay.
Rise. If it's odd, what's your left side doing?
Falling.
Falling. Okay? And you would just base it off of what you already answered for number 1. Okay, is it the same or is it opposite? Okay. But you're going to write it in mathematical notation. That's going to be the hard part. Okay, so let's look at an example. This is that same problem, right? From my very first slide when we named the degree and the leading coefficient. You guys are doing a great job. I know there's a lot of information on this first set of notes, so thanks for sticking with me. Tomorrow we'll kind of like have this part down, so then we can do a little bit less. Okay, so this is f of x equals x cubed minus x squared plus x minus 5. It's always a good idea, especially in the beginning here, to double check, is the polynomial in standard form, but we had already decided, yes it was, right? And we had also talked about in standard form, to do the degree and the leading coefficient, we would look at that very first term. So we said already that the degree was 3 and the LC was 1. Do you remember that? That's the one that we did together. So we can plug those things in. Okay. Degree was 3. LC was 1. What's the type of function that is? Luke? Cubic. You're naming the type by degree, right? So you look at that list, we've got constant, linear, quadratic, cubic, quartic, quintic. If it's something higher than that, then you say 6th degree, 7th degree. So the type is cubic. What about the total number of zeros, Jet?
Is it 3?
It's 3. It's equal to the
Degree.
degree. So we're just trying to make the little synapses in our brain connect today so that we know the total zeros is equal to the degree. What about the maximum number of turns? Palin says 2. What little connection are you using for max turns? Degree minus 1. So the total zeros is the degree. The max turns is the degree minus 1. Okay, this is going to be a hard one for tonight. And behavior. What side do we do first?
Right side.
The right side. So I'm going to say, as x approaches infinity, goes to the right. Y goes, and I've got to fill in that blank, right? So, I better bring this down so I can see. Now I'm utilizing my leading coefficient test. The first thing I do is look at my leading coefficient. It is positive. Therefore, the right side is rising, going up. So y approaches positive infinity. That says, to me, the right side rises, goes up. Luke?
Is that how you're supposed to write
Yep.
it? It is?
That's the mathematical notation. Okay. And then you do a second one for the left side as x approaches negative infinity. So like this is going to be challenging for us. We got to kind of get used to those 4 words and what their symbols are, right? As x approaches negative infinity, that's to the left. And now we have to decide in step 2 of the leading coefficient test, is it doing the same thing or something different? So if our degree is 3, it's opposite. Odd is opposite. So we'll say y is approaching negative infinity. This one's positive, so this one's negative. If it was supposed to be the same, I would just say positive right there. And then last y-intercept, 0, negative 5. That was our constant that we identified at the very beginning. Now, when you look at your gold sheet, notice it says like for 3 through 8. I am giving you a different set of instructions than the textbook. So the textbook just asks you like, is it a polynomial? And then it does like different characteristics later on. Let's just do less problems, but do all the things. So for like the required ones, 3, 5, 6, 7, if it is a polynomial, please do all these things that you see in your notebook. If it's not a polynomial, you can say no and move on. Does that make sense? Okay. And then we didn't get through like the increasing and decreasing. So that would be, I think it's number 33 and 35. Read it. You can look in the textbook at the example and try to answer it. We can also talk about it at the beginning of class tomorrow because we're going to be graphing it. So if that part's really worrying you, don't worry about it. We didn't get to it today. I will pass back your midterms tomorrow.